Hello and welcome to Science Night Tales. I am glad you have found this quiet moment to drift. Tonight, we are going to travel past the warmth of the sun, beyond the rocky worlds we know, and into the deep, cold architecture of the outer solar system. We often think of space as silent and still, but the giant planets tell a different story. They are worlds of endless storms, hidden oceans, and energy that refuses to settle. We will look at how scientists learn to navigate these distant realms, not by conquering them, but by understanding the delicate balance of gravity and motion. You do not need to memorize orbital mechanics tonight. You can simply let the scale of these worlds wash over you. The planets are turning, the moons are dancing, and you are safe to observe from a distance. If this perspective helps you feel grounded in the vastness, you are welcome to like or subscribe. For now, let go of the day and let's drift outward together. For centuries, the solar system appeared orderly, a central star, a set of planets arranged in calm, predictable paths. The inner world small and dense, the outer worlds distant and massive. Everything seemed to fit an intuitive logic. Heat close to the sun, cold far away. Solid near the center, gaseous at the edge. But this logic concealed a deeper problem. Between Mars and Jupiter lies a wide region filled not with planets, but with fragments. Millions of bodies, each following its own path, together forming what we now call the Asteroid Belt. A boundary, a discontinuity, a place where a planet was expected but never formed. And for a long time, that absence troubled scientists more than any discovery ever could. Because incomplete systems do not remain incomplete by accident. They remain incomplete because the conditions that shape them are more complex than we first assume. This is where the story of the outer planets truly begins. Not with spacecraft, not with technology, but with a failure of understanding. At first glance, the architecture of the solar system appears balanced. 4 small rocky planets orbit close to the sun. Beyond them, 4 giant worlds dominate the outer region. Between these 2 domains lies a wide, sparse zone filled with debris. This arrangement suggests a simple story. Close to the sun, temperatures were too high for gases to condense, leaving only metals and silicates to build planets. Farther away, ices and gases survived, allowing massive worlds to grow. This explanation is broadly correct, but it does not explain why the transition between these 2 regimes is so abrupt. Why do small rocky planets end at Mars? Why does Jupiter begin so suddenly with a mass greater than all other planets combined? And why does the region between them contain not a world, but a fragmented population of remnants? Early astronomers believed this region should contain a planet. They expected planetary systems to form smoothly, with mass distributed gradually as distance increased. The presence of a gap contradicted this assumption. For a time, the asteroid belt was interpreted as the remains of a destroyed planet, a world that once existed, a world that somehow broke apart. This idea persisted, not because evidence supported it, but because human reasoning tends to prefer catastrophic explanations when continuity is disrupted. A missing planet suggested an event suggested drama, drama suggested meaning. But as measurements improved, a quieter explanation emerged. The belt never held enough material to form a planet. From the beginning, the region was dynamically unstable. Jupiter's gravity disturbed the growth of planetary embryos. Resonances injected energy into forming bodies. Collisions became destructive rather than constructive. Instead of accreting, material fragmented. Instead of stabilizing, orbits became scattered. What remained was not a ruin, it was a boundary condition, a region where the rules of accumulation changed. This distinction is subtle but essential. The asteroid belt is not evidence of destruction, it is evidence of competition. Competition between gravity and motion, between growth and dispersion, between order and instability. In planetary systems, formation is not guaranteed. It depends on timing, on mass distribution, on the influence of neighboring giants. A small shift in any of these variables can prevent a planet from ever forming. This realization forced scientists to confront a deeper problem. If planetary systems depend so sensitively on early conditions, then stability itself may be rare. The solar system, long assumed typical, might instead be an unusually well-balanced outcome of competing forces. And the asteroid belt, rather than a minor feature, became a visible record of this delicate balance. A place where structure failed to complete itself. For human observers, such regions are psychologically powerful. We are unsettled by gaps, by interruptions, by systems that appear unfinished. Where continuity breaks down, curiosity intensifies. Incomplete patterns invite explanation. Boundaries invite crossing. The belt, therefore, became more than a physical region. It became a conceptual threshold. Beyond it lay worlds whose formation obeyed different rules, different chemistry, different energy regimes, different histories. To understand the solar system as a coherent system, that threshold had to be crossed, not because it was dangerous, but because it represented the first visible limit of our existing models. Modern planetary science describes formation as a sequence of competitive processes. A cloud of gas collapses, angular momentum redistributes, a disk forms, solid grains condense, planetesimals collide, embryos grow, gas accretes or escapes. Each step is sensitive to timing. If gas dissipates too quickly, giants cannot form. If embryos grow too slowly, they are scattered. If resonances emerge early, entire regions become unstable. The inner planets formed in a high-temperature, low-gas environment. The outer planets formed in a colder, gas-rich zone. But the transition between these zones was not smooth. Jupiter formed early and grew rapidly. Its gravity reshaped the disk before Mars could accumulate sufficient mass. Material that might have built a fifth terrestrial planet was instead dispersed. Mars remained small. The belt remained fragmented. In this sense, the architecture of the solar system is not symmetrical. It is the frozen record of an early gravitational imbalance. This insight has consequences far beyond our system. If giant planets commonly form early and migrate, then many planetary systems may be violently restructured before smaller worlds can stabilize. Some may lose inner planets entirely. Some may scatter material into wide belts. Some may eject worlds into interstellar space. Our solar system's relatively calm inner region may therefore be exceptional. And its outer giants, rather than guardians, may represent an early disruptive phase that only later settled into long-term stability. This reframes the asteroid belt once again, not as an accident, not as a failure, but as a surviving trace of instability that never fully resolved. When the first interplanetary missions were conceived, engineers did not see the belt as a graveyard. They saw it as a statistical problem. How many objects occupy the region? How large are they? How are they distributed? As data accumulated, one conclusion became unavoidable. the belt is sparse, collisions are unlikely, trajectories can be planned with negligible risk. Physically, it was no longer a barrier, but symbolically, it remained important. Crossing the belt meant leaving the domain of terrestrial planets. It meant entering a region governed by different physical regimes, different pressures, different temperatures, different magnetic fields, different energy sources. The decision to send spacecraft beyond this boundary was therefore not simply exploratory, it was methodological. It tested whether planetary science could operate as a unified discipline across radically different environments. Could one theory explain both rocky crusts and gaseous envelopes? Could one model describe both frozen moons and volcanic satellites? Could one framework account for both geological stillness and continuous internal heating? The outer planets offered a natural laboratory for these questions, not because they were exotic, but because they represented extreme versions of familiar processes. Gravity at large scale, atmospheres under high pressure, tidal forces operating continuously. To understand them was to test the limits of planetary physics itself. As missions were planned and trajectories calculated, the stated goals focused on mapping, imaging, and sampling. But beneath these operational objectives lay a deeper purpose. The exploration of the outer planets was not about distance, it was about persistence. How does structure endure in environments where equilibrium is constantly disrupted? How do large systems remain coherent when internal and external forces operate continuously? How does complexity survive without collapsing into disorder? These questions apply not only to planets, but to systems in general. Atmospheres, magnetospheres, orbital resonances, thermal cycles. In each case, stability is not static. It is maintained through constant energy exchange. A planet remains active because heat flows. A moon remains warm because tides dissipate energy. A magnetic field persists because charged particles circulate. Where energy ceases to flow, complexity decays. This principle would soon redefine expectations about habitability. Life, it would become clear, does not require a temperate surface. It requires gradients, interfaces, continuous disequilibrium. Liquid water alone is insufficient. Chemical complexity alone is insufficient. What matters is sustained energy flow across boundaries. The outer planets offered environments where this condition could be tested in unfamiliar forms. Subsurface oceans beneath ice, tidal heating without sunlight, where atmospheres driven by internal convection rather than stellar radiation. These were not marginal cases. They were systematic alternatives to terrestrial conditions. In this sense, the outer planets were not distant targets. They were experimental systems. Each moon, each ring, each magnetosphere represented a controlled variation on fundamental physical principles. By studying them, scientists were not merely cataloging features, they were probing the general laws that govern complex systems under constraint. Three questions emerged and would recur throughout every mission. How do large systems remain stable over billions of years? Gravity alone does not guarantee coherence. Resonances can amplify motion. Energy can destabilize or regulate depending on how it is distributed. Understanding stability required tracing the balance between accumulation, dissipation, and resonance. How does energy shape planetary behavior? Thermal gradients drive circulation. Tidal forces generate heat. Radiation interacts with atmospheres. Energy determines geology, weather, magnetism, and chemistry. And where energy persists, activity follows. Where can life persist beyond familiar conditions? Not where temperatures are comfortable, not where sunlight is abundant, but where chemical reactions are sustained far from equilibrium, where interfaces exist between solid, liquid, and gas, where energy flows slowly but continuously. These were the hidden questions that guided exploration. Not beauty, not spectacle, but survival, persistence, stability under constraint. As spacecraft began their journeys, the models that had seemed complete were already under strain. The asteroid belt had revealed that planetary systems are not smooth. Jupiter had revealed that giants reshape entire architectures. Mars had revealed that small worlds can lose their internal engines early. What remained unknown was whether complexity could persist in colder, darker regions. Could internal heating compensate for lack of sunlight? Could chemistry remain active beneath ice? Could systems remain dynamic for billions of years without external input? The outer planets would soon answer these questions, not through singular revelations, but through accumulation, through slow mapping, through repeated measurements, through long-term monitoring. The discoveries would not arrive as dramatic events. They would arrive as corrections. Corrections to assumptions about geological lifetimes. Corrections to assumptions about thermal balance. Corrections to assumptions about where life might exist. And gradually, without proclamation, a new view of planetary systems would take shape. One in which stability is rare. One in which complexity depends on constant disequilibrium. One in which habitable environments may exist far from stars. This transformation did not begin with a search for wonder. It began with an attempt to explain an absence, a gap between Mars and Jupiter, a region where a planet never formed, and a realization that systems reveal their deepest laws, not where structure is complete, but where it fails to complete itself. Beyond that boundary, a different regime awaited, and with it, a revision of how planets, energy, and life itself must be understood. Before spacecraft carried instruments beyond Earth, the outer solar system existed almost entirely as an intellectual construct. Astronomers did not observe planets directly in any detailed sense. They inferred them from faint points of light, from blurred disks distorted by Earth's atmosphere, from subtle shifts in spectra measured through imperfect glass. What scientists believed about Jupiter, Saturn, and the regions beyond was not the result of close inspection. It was the product of mathematical reconstruction. Planetary science, in its early form, was not an observational discipline. It was an inferential one, and inference, by necessity, simplifies what cannot yet be resolved. For most of human history, the outer planets were inaccessible not because of distance, but because of resolution. Even with the largest ground-based telescopes of the early 20th century, Jupiter and Saturn appeared as soft, unstable disks. Atmospheric turbulence blurred fine detail. Short exposure times limited clarity. Instrumental noise obscured faint structures. What could be seen reliably were only the largest features: Jupiter's banded appearance, Saturn's rings as a continuous bright ellipse, the Galilean moons as moving points, Titan as a faint orange dot. Everything else was conjecture. Yet from these limited observations, astronomers attempted to reconstruct the internal nature of worlds thousands of millions of kilometers away. They measured brightness to estimate albedo. They measured orbital motion to estimate mass. They analyzed spectral lines to infer composition. Each step relied on assumptions. Brightness depends not only on reflectivity, but on atmospheric scattering. Mass estimates depend on orbital perturbations that may involve unseen bodies. Spectral absorption depends on temperature, pressure, and line-broadening mechanisms that were poorly constrained. In effect, each parameter was solved by assuming the others. This circular dependence shaped early planetary models. The dominant conclusion was simple and reassuring. The outer planets were cold, they were inactive, they were chemically simple, they were geologically frozen. This view did not arise from evidence of stillness. It arose from the absence of evidence for activity. From Earth, volcanic plumes could not be detected. Subsurface oceans could not be inferred. Internal heat sources could not be measured, and so they were assumed not to exist. The prevailing model treated the outer planets as thermodynamically exhausted systems, large, gaseous bodies that had cooled since formation, moons that had frozen solid early in their histories, atmospheres driven primarily by external solar heating rather than internal convection. This model reflected a broader assumption in early planetary science. That activity requires sunlight, that geology requires warmth, that chemistry slows rapidly in cold environments. The inner planets, warmed by the sun, were considered dynamic. The outer planets, deprived of radiation, were assumed to be inert. This belief seemed reasonable. Thermodynamics predicted that without sustained energy input, systems approach equilibrium, and equilibrium implies uniformity. Uniformity implies stillness. The mistake lay not in the physics, but in the boundary conditions. Early models considered only stellar radiation as a viable energy source. They largely ignored tidal dissipation. They underestimated radioactive heating. They did not yet understand magnetospheric coupling. As a result, they assumed that distance from the Sun directly determined geological and atmospheric activity. Cold meant dead. This assumption was not tested, it was inherited. Before spacecraft, planetary mass was inferred almost exclusively from orbital dynamics. The gravitational influence of a planet on its moons provided estimates of total mass. But mass alone does not determine structure. To estimate density, astronomers combined mass with radius. But radius measurements were imprecise. Atmospheric refraction blurred planetary edges. Rotation induced flattening, distorted silhouettes. Even small errors propagated into large uncertainties in density. Composition estimates were even more indirect. Spectroscopy identified broad absorption features associated with hydrogen, helium, methane, ammonia, and water vapor. But pressure broadening made line identification ambiguous. Temperature uncertainties affected molecular equilibrium. Cloud layers obscured deeper atmospheric chemistry. For moons, the situation was worse. Their spectra were faint, their surfaces unresolved, their internal structures unknowable. Most were assumed to be solid, frozen bodies with little differentiation. When astronomers discussed the internal evolution of moons, they relied on simplified cooling models. Small bodies lose heat quickly. Radioactive heating declines with time. Without tidal input, internal activity should cease early. This reasoning appeared consistent. It was also incomplete because it treated moons as isolated systems. In reality, moons in resonance exchange energy continuously. Orbital eccentricity sustains deformation. Deformation generates heat. Heat maintains liquid layers. This feedback was not fully appreciated until spacecraft measurements revealed its magnitude. But before those measurements, stillness remained the default assumption, not because it was proven, but because it was the least complex explanation. Early planetary models favored equilibrium for reasons that extended beyond physics. Equilibrium is mathematically stable. It simplifies long-term predictions. It reduces computational complexity. But it also satisfies a psychological preference. Humans prefer systems that settle, that evolve toward rest, that reach completion. In dynamic systems that remain perpetually active are harder to conceptualize. They resist closure. They require continuous explanation. In the absence of evidence to the contrary, equilibrium becomes attractive. Thus, the outer solar system was pictured as a completed architecture. Formation had ended, cooling had progressed, activity had ceased. The giants were mature, their moons ancient and frozen. This view dominated textbooks well into the mid-20th century. It shaped mission planning. It influenced instrument design. It framed scientific expectations. The outer planets were considered valuable primarily as records of early composition, not as active laboratories. Distance played a central role in shaping these assumptions. Far objects are difficult to observe. Poorly observed objects are assumed to be simple. This bias recurs throughout the history of science. Distant stars were once assumed to be uniform. Distant galaxies were once assumed to be static. Distant continents were once assumed to be empty. Complexity is usually discovered only after proximity improves. Before spaceflight, proximity to the outer planets was impossible. Thus, simplicity prevailed by default. The outer solar system became, in the scientific imagination, a region of large but uneventful bodies. Impressive in scale, unremarkable in behavior. This expectation would soon collapse. But before it did, another region exerted a powerful influence on human perception. A region much closer, much smaller, and far more psychologically charged. The asteroid belt occupies a narrow range of orbital distances between Mars and Jupiter. In absolute terms, it contains little mass, less than 1,000th of Earth's mass, distributed across millions of bodies. Physically, it is sparse, but psychologically, it was dense with meaning. From the moment asteroids were first catalogued, the belt acquired an ambiguous status. It was neither planet nor void, neither complete system nor empty space. It appeared as a transitional region where planetary formation had stalled, and transitions tend to attract anxiety. Early estimates of asteroid density varied widely. Some astronomers imagined a crowded swarm. Others pictured isolated fragments separated by vast distances. Without direct sampling, the true distribution remained uncertain. When interplanetary missions were proposed, this uncertainty acquired operational significance. If the belt were dense, collisions could be catastrophic. If populated by unseen debris, navigation could be hazardous. The statistical reality was difficult to communicate. Even a sparse distribution, when extended across millions of kilometers, suggests inevitability rather than improbability. Humans tend to reason linearly about risk. A region filled with many objects seems dangerous, even when the volume is vast and occupancy minimal. Probability, when applied to unfamiliar scales, loses intuitive meaning. Thus, the belt came to be perceived not as empty, but as threatening. This perception was amplified by early science fiction and popular media. Asteroid fields were depicted as dense clouds of tumbling rocks. navigation was portrayed as continuous evasion. Collisions appeared unavoidable. These images had little relation to physical reality, but they shaped public imagination. They also influenced early engineering conservatism. Mission designers responsible for unprecedented hardware tended to overestimate unknown risks. Shielding was considered. Redundancy increased. Trajectory margins widened. The belt was treated as a potential failure point, not because data demanded it, but because uncertainty invites caution. Beyond physical risk, the belt acquired symbolic weight. It represented the first region beyond planetary familiarity, the first boundary where orderly orbits gave way to scattered debris. To cross it was to leave behind the region shaped primarily by solar gravity and enter one shaped strongly by a giant planet. This transition mattered scientifically. Inside the belt, planetary dynamics are relatively simple. Outside it, resonances dominate. Gravitational perturbations become continuous. Orbital evolution becomes long-term and coupled. Thus, the belt marked not only a physical boundary, but a dynamical one. Different regimes of motion, different timescales of stability, different modes of evolution. Crossing it symbolized entry into a more complex gravitational environment. In this sense, the belt's significance was methodological rather than operational. It represented the point where planetary science would confront multi-body dynamics directly, where linear approximations would fail, where long-term integrations would be required. This raised deeper questions. Could trajectories remain stable over decades? Could instruments survive extended exposure to radiation? Could navigation remain precise when gravitational influences multiplied? The belt condensed many uncertainties into a single region, not because it was uniquely dangerous, but because it was where simple models ended. Public perception further intensified the belt's psychological role. Journalistic accounts emphasized hazard, illustrations exaggerated density, narratives framed crossing as heroic. This framing served a purpose. It dramatized exploration. It justified expense. It elevated engineering achievement. But it also distorted understanding. The belt became a test of courage rather than a test of probability. This mattered because it shaped how the first successful crossings were interpreted. When Pioneer 10 passed through the belt without incident, headlines described triumph. Yet scientifically, the outcome was expected. The crossing validated models that already predicted low risk. What it truly accomplished was not survival. It produced empirical density measurements, dust impact counts, particle flux distributions, size frequency estimates. These data transformed the belt from imagined obstacle into quantified environment. But the deeper achievement lay elsewhere. Pioneer 10 reframed the belt as a controlled experiment in probabilistic navigation, a test of whether statistical predictions about sparse systems would hold at interplanetary scale. And they did. This result had implications far beyond asteroid dynamics. It validated the use of probabilistic modeling for long-duration missions. It reduced perceived risk for all subsequent trajectories. It enabled complex gravity assist planning. The belt ceased to be a barrier, not because it was conquered, but because it was measured. With the belt quantified and crossed, a transition occurred in planetary science. The discipline began to move from inference toward observation. Dust detectors replaced speculation. Trajectory tracking replaced fear. Statistical distributions replaced anecdote. This transition mattered profoundly for what would follow. If the belt could be understood through direct measurement, then so could the outer planets. If sparse systems could be navigated reliably, then complex gravitational environments could be explored. The psychological barrier dissolved, but its influence lingered. For decades, scientists had assumed the outer solar system to be static and inert. The belt reinforced this view by suggesting that activity was confined to inner regions. Once this assumption fell, the stage was set for a deeper revision. The outer planets would soon reveal not stillness, but continuous energy flow. Not simplicity, but layered complexity. Not equilibrium, but long-lived disequilibrium. Before spacecraft, none of this was visible. The models were internally consistent. The assumptions felt reasonable. The silence of distant worlds seemed complete. But silence, when observed from far away, often reflects not stillness, but distance. And as instruments closed that distance, the outer solar system would begin to contradict nearly every expectation that had been built upon inference alone. The decision to explore the outer planets was not driven by spectacle, it was driven by necessity. By the middle of the 20th century, planetary science faced a structural limitation. Observations of the inner planets were improving. Radar mapping advanced. Geological models matured. Comparative planetology began to take shape, yet the outer planets remained conceptually distant, not only in kilometers, but in explanatory value. Scientists increasingly realized that without understanding the giants and their moons, the solar system itself could not be explained as a coherent system. The inner planets represented outcomes, the outer planets preserved conditions, and the difference between those two categories would soon become decisive. At the most basic level, the outer planets contain most of the mass of the solar system outside the Sun. Jupiter alone holds more than twice the mass of all other planets combined. This fact alone carries implications. Where mass accumulates, gravity dominates. Where gravity dominates, structure follows. Where structure follows, history is preserved or erased depending on internal activity. The gas giants therefore occupy a privileged position in planetary science. They are not simply additional worlds, they are primary regulators of the system's architecture. The outer planets formed while the solar nebula still retained most of its primordial gas. Hydrogen and helium, which escape readily from smaller bodies, remained gravitationally bound to the giants. Volatile compounds condensed into deep atmospheres. Ices accumulated in massive envelopes. In effect, these planets incorporated material from the earliest chemical inventory of the solar system. Unlike terrestrial planets, they did not lose this inventory through surface recycling. On Earth, crustal motion continually renews the surface. Volcanism remelts material. Weathering redistributes elements. The impacts are buried or erased. After a few 100 million years, little direct evidence of formation remains accessible. By contrast, the outer planets lack solid surfaces in the conventional sense. Their atmospheres preserve deep chemical signatures. Their internal layers remain stratified. Their elemental ratios record conditions from the time of accretion. This made them uniquely valuable. They were not only planets, they were chemical archives. By measuring isotopic abundances, noble gas ratios, and volatile distributions, scientists could reconstruct the composition of the early solar nebula. This information could not be recovered reliably from any inner planet. Thus, the giants offered a way to test formation models directly, not by inference from eroded surfaces, but by sampling preserved material. If the giants preserved composition, their moons preserved diversity. The satellite systems of Jupiter and Saturn contain dozens of bodies spanning a wide range of sizes, densities, and orbital configurations. Some are rocky, some icy, some differentiated, some irregular, all formed in the same gravitational environment. This configuration provides a controlled experiment: shared origin, shared central mass, shared radiation field, different outcomes. From a scientific perspective, this is unusually valuable. By comparing moons within a single system, researchers can isolate the effects of size, composition, and orbital energy. Why does one moon remain inert while another remains active? Why does one differentiate while another remains undifferentiated? Why does one retain an atmosphere while another loses it? These questions cannot be addressed effectively by comparing unrelated planets. They require systems in which many variables are shared. The giant planet satellite systems provide exactly this condition. In this sense, moons are not secondary targets. They are primary experimental platforms. They allow planetary science to move from descriptive cataloging toward causal analysis. Beyond composition and diversity, the giants exert a systemic influence that no other planets approach. Their gravity shapes the distribution of small bodies. It defines resonance zones. It controls long-term orbital stability. It influences impact rates throughout the inner system. In effect, the giants function as structural anchors. They regulate angular momentum. They shepherd debris. They destabilize some regions while stabilizing others. This has consequences for planetary survival. Simulations show that without Jupiter, the inner solar system would experience higher impact rates. But with Jupiter migrating differently, terrestrial planets might never form at all. The giants are therefore not passive residents. They are active architects. To understand the long-term evolution of planetary systems, one must understand how massive planets shape their environments. This insight acquired new importance as exoplanet discoveries accumulated. Hot Jupiters, eccentric giants, migrating planets. Many systems appear radically different from ours. Understanding our own giants became essential for interpreting these unfamiliar architectures. Without that understanding, exoplanet statistics would remain disconnected from formation theory. The concept of planetary memory lies at the core of this scientific motivation. Some bodies preserve history, others erase it. On Earth, plate tectonics destroys ancient crust. On Venus, resurfacing events renew the landscape. On Mars, erosion and volcanism blur early records. These processes erase information. They simplify surfaces over time. The outer planets, by contrast, operate under different constraints. They lack solid crusts capable of tectonic recycling. Their atmospheres mix slowly. Their interiors evolve on long thermal timescales. As a result, their large-scale structure retains signatures of early conditions. Layering patterns record accretion history. Elemental gradients reflect condensation sequences. Isotopic ratios preserve nebular chemistry. Their moons also preserve memory. Icy surfaces remain stable for billions of years. Impact craters accumulate rather than disappear. Internal layers cool slowly. In many cases, the present state of a moon still reflects its formation energy and early heating history. Thus, the outer solar system functions as a geological archive on a scale unavailable elsewhere. To ignore it would be to ignore the only accessible record of the solar system's earliest epoch. This contrast explains why the inner planets cannot serve the same role. Their small size leads to rapid cooling. Their higher temperatures drive active geology. Their atmospheres promote chemical alteration. Over time, surfaces are renewed, crust is recycled. Mantle convection redistributes material. The record becomes fragmentary. On Earth, rocks older than 4 billion years are rare. On Venus, none are accessible. Though on Mercury, resurfacing has modified much of the terrain. The inner planets therefore preserve only partial histories. They reveal outcomes, but they do not reliably reveal processes. The outer planets, by contrast, preserve both. They retain chemical fingerprints of accretion. They maintain internal heat from formation. They preserve orbital architectures established early. In this sense, they are not merely distant. They are temporally closer to the origin of the system than any terrestrial world. To study them is to study the solar system in a less evolved state. This realization transformed mission priorities. The outer planets were no longer optional targets, they were essential. Scientific motivation alone does not determine mission feasibility. Trajectories require energy. Energy requires propulsion. Propulsion requires mass. Mass requires launch capability. For most of the 20th century, reaching the outer planets with chemical rockets was impractical. Direct trajectories to Jupiter demanded high launch energy. Reaching Saturn, Uranus, and Neptune in sequence was beyond reach. Then a rare configuration emerged, a geometric alignment of the outer planets that occurs approximately once every 176 years. During this alignment, the giant planets arrange themselves so that a spacecraft leaving Earth can encounter each in sequence using gravitational assists. This opportunity was not immediately obvious. It required the development of patched conic trajectory theory and numerical integration techniques. When the alignment was recognized, its significance was profound. With gravity assists, a single spacecraft could visit multiple planets using minimal onboard fuel. Energy could be borrowed from planetary motion. Velocity could be redirected rather than generated. The energy economy changed completely. Gravitational assist works by exchanging momentum between a spacecraft and a moving planet. From the planet's frame, the spacecraft follows a hyperbolic trajectory. From the Sun's frame, the spacecraft gains or loses velocity depending on geometry. The key principle is that energy is transferred from the planet's orbital motion to the spacecraft. The planet loses an infinitesimal amount of momentum. The spacecraft gains a significant change in trajectory and speed. This technique allows large velocity changes without fuel expenditure, but it imposes strict constraints. Arrival times must coincide precisely with planetary positions. Approach angles must fall within narrow corridors. Small errors amplify over long durations. The alignment provided a sequence of planets positioned favorably for repeated assists. Earth to Jupiter, Jupiter to Saturn, Saturn to Uranus, Uranus to Neptune. Miss the window and the opportunity vanishes for generations. The alignment created a unique strategic situation. With existing launch vehicles, only this window made a multi-planet mission feasible. Without it, each planet would require a dedicated mission. Costs would multiply, timescales would extend. The scientific community faced a binary choice: act within this window, or postpone comprehensive outer planet exploration for more than a century. Such postponement was effectively permanent within any human planning horizon. This temporal constraint forced an unusual concentration of ambition. Rather than incremental missions, planners proposed an integrated program. One sequence, one architecture, one generation of spacecraft. This would later become the Voyager program. But at the time, nothing of that scale had been attempted. The risk was substantial. Failure would compromise decades of opportunity. Success would redefine planetary science. NASA approached the problem cautiously. Budgets were limited, launch reliability uncertain, deep space communication immature, radiation environments poorly understood. The agency faced competing priorities: human spaceflight, Earth observation, defense-related missions. Outer planet exploration offered high scientific return but high uncertainty. Cost overruns were likely. Mission durations would exceed political cycles. Failures would be difficult to recover from. Risk analysis therefore played a central role. Engineering teams assessed radiation damage near Jupiter. Navigation teams evaluated cumulative trajectory errors. Communication specialists modeled signal attenuation at extreme distances. Every subsystem faced unknowns. Yet the alignment imposed urgency. Delay meant forfeiture. The institutional calculus shifted. Instead of minimizing risk by postponement, NASA accepted risk to preserve opportunity. This decision was unusual. Large organizations tend to avoid time-constrained gambles. But here, the asymmetry was clear. Act now and risk failure, or wait and guarantee ignorance. The scientific case prevailed. The alignment coincided with a transitional period in space policy. Apollo was nearing completion. Human exploration budgets were declining. Public attention was shifting. Planetary science needed a new flagship program to maintain momentum. The Grand Tour offered such a program. It provided continuity. It justified infrastructure. It aligned with long-term scientific goals. Political timing proved favorable. Funding could be reallocated from lunar programs. Launch facilities remained active. Expert teams were available. Had the alignment occurred earlier, resources would have been absorbed by Apollo. Had it occurred later, institutional momentum might have dissipated. This convergence of celestial geometry and political circumstance was rare, and it would not repeat. Beyond technical and institutional factors, a psychological element shaped the decision. Humans respond strongly to rare opportunities. Scarcity intensifies commitment. Deadlines sharpen priorities. Irreversibility encourages boldness. The alignment created a perception of singularity. One chance, one sequence, one generation. This framing influenced scientists, engineers, and administrators alike. Proposals became more ambitious, architectures more integrated. Risk tolerance increased. The missions were no longer incremental probes. They became generational projects, designed not only to answer existing questions, but to anticipate future ones. Instrumentation was diversified, data rates increased, longevity extended. The goal was not merely to reach the planets, it was to create a lasting scientific platform. The alignment shaped mission design in fundamental ways. Spacecraft had to be capable of surviving decades. Power systems had to operate far from the sun. Instruments had to remain functional long after launch. This forced innovation. Radioisotope generators replaced solar panels. Autonomous fault protection was developed. Long baseline communication techniques matured. These technologies would later enable missions far beyond the original scope. In this sense, the alignment not only enabled exploration, it catalyzed a new technological regime in deep space science, and with that regime came a transformation of expectations. The outer planets were no longer distant curiosities. They became central to understanding planetary systems as dynamic, evolving, and structurally constrained entities. The decision to exploit this rare geometry would soon yield results that no inference-based model had anticipated. And with each encounter, the quiet assumption of stillness would give way to a far more complex reality. Before humanity could reach the outer planets, it first had to confront a simpler and more unsettling problem. Not how to build engines powerful enough, not how to communicate across vast distances, not how to survive radiation or cold. It had to decide whether interplanetary space itself could be trusted. Between the inner planets and Jupiter lay a region that no machine had ever crossed, the Asteroid Belt. Not physically dense, not measurably violent, but psychologically heavy with uncertainty. By the early 1970s, theoretical models suggested that this region should be sparse. Astronomers estimated the number of large asteroids through telescopic surveys. Brightness distributions hinted at size-frequency relationships. Perturbations in planetary motion constrained the belt's total mass. From these indirect measurements, scientists built statistical models of spatial density. They assumed random distributions within orbital zones. They incorporated relative velocities and cross-sectional encounter areas. They calculated expected impact rates per unit distance. The results were reassuring. Collisions with large objects were essentially impossible. Encounters with centimeter-scale debris were unlikely to be destructive. Micrometeoroid flux was expected to be continuous but mild. Yet reassurance did not remove unease, because low probability does not eliminate consequence. And because no spacecraft had ever tested these assumptions directly, engineers faced a new category of uncertainty. They were not protecting against mechanical failure. They were protecting against an environment that had never been measured. The belt could not be reproduced in laboratories. It could not be observed with sufficient resolution. It could not be simulated with confidence. Instead, it had to be trusted statistically. Pioneer 10 carried instruments designed to sample this unknown medium. Dust detectors to record impact frequency and momentum. Penetration sensors to register micrometeoroid strikes. Plasma instruments to measure charged particle density. But these instruments had limits. They could not detect the smallest grains. They provided limited directional information. They inferred velocity indirectly. The telemetry bandwidth was low. Storage capacity was minimal. Real-time intervention was impossible. If a catastrophic impact occurred, it would be known only after silence followed. The crossing would not be navigated, it would simply be endured. Engineers accepted this because there was no alternative. Shielding against all conceivable debris would make the spacecraft too heavy to launch. Detecting and avoiding small bodies was beyond available technology. Survival depended on one premise. That space, even when populated, is overwhelmingly empty. This required a subtle change in engineering philosophy. Instead of designing against worst-case scenarios, they designed against expected distributions. Instead of eliminating uncertainty, they quantified it. The mission was approved not because risk vanished, but because risk could be expressed numerically. Uncertainty became manageable once it was measured. Pioneer 10 entered the asteroid belt late in 1972. For months, it passed through the region of highest expected density. Impact counters registered occasional micrometeoroid strikes. dust detectors measured low-level flux. No significant collisions occurred, but the importance lay not in survival, it lay in agreement. Observed particle densities matched predicted values. Size distributions followed. Expected trends. Temporal variations remained within modeled limits. The environment behaved exactly as probability had described it. This outcome lacked drama. No evasive maneuvers were needed. No emergency commands were sent. No crises unfolded. Yet scientifically, it was decisive. For the first time, the deep space risk model had been validated by direct sampling. Interplanetary space was not hostile, it was sparse. This single confirmation altered mission planning permanently. Shielding requirements relaxed, mass budgets improved, payload capacities increased. Dust models were extended beyond the belt. Radiation predictions improved. Navigation tolerances widened. The belt ceased to be a special region. It became ordinary space. With that shift came new ambition. Gravity-assist trajectories became acceptable. Multi-planet tours became feasible. Decades-long missions became credible. Without this validation, such architectures would have remained politically and institutionally fragile. More importantly, engineering culture changed. Unknown environments were no longer treated as hazards. They were treated as statistical fields. Risk assessment became quantitative. Design became probabilistic. Optimization replaced overprotection. This transformation extended beyond this single mission. It shaped every outer planet mission that followed. But perhaps the deepest effect was psychological. Fear dissolved quietly. Mystery turned into calibration. The asteroid belt no longer symbolized danger. It symbolized the reliability of physical law across vast scales. Once that barrier dissolved, the remaining distances felt less forbidding. Jupiter no longer seemed unreachable. Saturn no longer seemed remote. The outer system no longer seemed speculative. The path outward had become trustworthy. Pioneer 10 did not reveal new worlds. It revealed that the way to those worlds obeyed rules we already understood. It replaced imagined obstacles with measured emptiness. It replaced narrative with probability. And with that quiet confirmation, the solar system beyond Mars ceased to be an unknown region. It became a navigable domain. Ahead lay worlds far more complex than any dust cloud. Worlds that would soon overturn the assumption that the outer planets were calm, frozen, and inactive. Worlds that would reveal motion where stillness had been expected, and instability where permanence had once seemed assured. Discovery in the outer solar system did not begin with images. It began with decisions about what could be measured at all. Every spacecraft carried a limited mass budget. Every instrument competed for power, volume, thermal stability, and data rate. Every measurement required sacrificing another. The architecture of discovery was therefore philosophical before it was technical. Spectrometers, magnetometers, imaging systems, plasma detectors, particle counters. Each instrument encoded a theory about what mattered. Infrared spectrometers prioritized thermal structure and composition. Ultraviolet instruments targeted atmospheres and magnetospheric interactions. Imaging systems sought morphology, motion, and change. But none could operate without constraint. Higher resolution demanded longer integration times. Higher sensitivity increased noise vulnerability. Broader wavelength coverage reduced spectral precision. Bandwidth limited how much information could be returned. Radiation limited how long electronics could survive. thermal gradients distorted calibration. Design became negotiation. Engineers balanced spatial resolution against temporal coverage, spectral depth against telemetry capacity, radiation shielding against mass limits. No instrument was ideal. Each represented an optimized compromise within institutional boundaries. Funding priorities shaped these choices directly. Flagship missions emphasized multi-purpose payloads. Discovery-class missions favored focused experiments. Political oversight encouraged redundancy and reliability over novelty. This affected what could be known. High-risk instruments were often excluded. Unproven technologies were delayed. Long-term measurements were favored over short-term precision. Scientific agendas followed architecture. Questions that matched available instrumentation advanced. Questions that required unavailable sensors waited decades. Even discovery itself became path-dependent. Once a payload was defined, the universe could only be observed through those channels, and interpretation followed. Spectra revealed composition only within selected bands. Magnetometers inferred interiors indirectly. Images emphasized morphology over chemistry. Understanding emerged not from the universe alone, but from the interaction between environment and instrument. This imposed a subtle filter on knowledge, not deliberate, not ideological, structural. The outer planets were therefore discovered through a constrained window of observables. Yet even within these limits, a second transformation proved equally important. Autonomy. As distances increased, light time delays expanded from minutes to hours. Commands could not be interactive. Intervention could not be timely. Spacecraft had to protect themselves. Fault detection systems monitored voltages, currents, temperatures, and processor states. Thresholds triggered safing routines. Instruments shut down automatically. Orientation changed to stabilize power and thermal balance. These systems were not intelligent. They followed deterministic logic trees, predefined priorities, conservative defaults. But their reliability determined mission survival. Because no human could respond quickly enough, risk management shifted fundamentally. Instead of preventing every fault, engineers assumed faults would occur. Instead of continuous control, they implemented layered protection. Redundancy became essential. Duplicate processors, backup transmitters, alternate star trackers. Yet redundancy consumed mass and power. Once again, compromise defined capability. Autonomy extended beyond fault protection. Sequencing systems executed observation plans over days or weeks. Attitude control systems corrected, pointing without guidance. Data compression algorithms prioritized which bits returned first. The spacecraft decided what to keep, not consciously, not selectively, but according to encoded rules about value. Bright features transmitted before faint ones. High-priority targets preempted background surveys. Health telemetry displaced science when margins narrowed. Discovery became conditional on machine judgment. This introduced a new psychological dimension. Engineers no longer controlled missions continuously. They delegated authority to systems that could not explain decisions. Trust became essential. Trust that fault logic would not trigger unnecessarily. Trust that compression would not discard crucial anomalies. Trust that navigation corrections would remain stable. This trust was not emotional, it was statistical. Validated through simulation, through hardware-in-the-loop testing, through probabilistic risk analysis. But it remained incomplete because no test could reproduce the exact radiation environment. No simulation could capture every failure mode. No ground experiment could model decades of degradation. Deep space required surrendering control gradually, and with that surrender came a shift in scientific culture. Missions were designed not as experiments, but as autonomous observatories. Researchers learned to analyze imperfect data, to infer from partial signals, to accept ambiguity as intrinsic. This altered interpretation. Anomalies were treated cautiously. Patterns required repeated confirmation. Claims remained conservative. The style of planetary science became shaped by machine limitations. Precision replaced speculation. Statistics replaced narrative. Ensemble modeling replaced single explanations. Yet these constraints also enabled new forms of knowledge. Long-term monitoring became possible. Continuous magnetospheric mapping, multi-year atmospheric studies, autonomy made endurance feasible. Voyager survived far beyond design life because its systems could protect themselves. Cassini operated for decades because its fault logic adapted to degradation. Juno navigated radiation belts because autonomy reduced ground intervention latency. Without autonomy, exploration would have ended near Mars. But autonomy introduced another boundary. Machines cannot redefine objectives. They cannot reinterpret anomalies. They cannot choose curiosity over safety. When unexpected phenomena appeared, humans still led interpretation. The machines observed, humans explained. This division shaped discovery profoundly. Instruments detected signals that no model predicted. Magnetometers recorded fluctuations without explanation. Images revealed surfaces without geological context. Only later did theory catch up. Thus, technology did not merely extend perception, it structured the order in which understanding developed. First observation, then anomaly, then interpretation, then revision of theory. This sequence repeated across missions. Io's volcanism appeared before tidal heating theory matured. Europa's ocean emerged before models of saline induction were complete. Enceladus's hydrogen was measured before hydrothermal circulation was accepted. Technology revealed effects before causes. This reversed classical scientific order. Hypothesis no longer preceded observation. Observation forced hypothesis. In this sense, spacecraft instruments became engines of epistemological change. They destabilized existing models. They created data beyond explanatory frameworks. They compelled theoretical expansion. And funding structures influenced which revolutions occurred first. Instruments designed to detect atmospheres revolutionized Titan. Magnetometers transformed Europa. Particle analyzers reshaped Enceladus. Entire subfields emerged from payload selections made decades earlier. Thus, the history of discovery became inseparable from institutional choice. Which missions were approved? Which instruments were funded? Which risks were tolerated? Even curiosity followed budget lines. Yet through all these layers, a final pattern remained. Machines extended human perception into regions unreachable by biology. But interpretation remained human. Meaning still depended on theory, on modeling, on cautious inference. The spacecraft did not reveal truths directly. They delivered signals, and from those signals, humans constructed knowledge, slowly, iteratively, conservatively. The outer planets were not discovered in moments of revelation. They were assembled gradually from telemetry streams, calibration curves, and probabilistic models. Each insight layered on the previous. Each anomaly refined understanding. And behind every image, every spectrum, every magnetic fluctuation stood a silent architecture of trade-offs. between mass and power, between risk and ambition, between precision and endurance. The technology did not merely carry science outward, it defined what science could become. And in doing so, it quietly demonstrated another principle. That exploration is not limited by distance alone. It is limited by the design of the tools with which we choose to see. Voyager did not set out to create an icon. It was built to measure magnetic fields, plasma densities, charged particles, and planetary atmospheres. Its cameras were secondary instruments. Its imaging system was designed for flybys, not reflection. Yet one of its most enduring contributions would arrive not from a new discovery, but from a decision about framing. At the edge of the solar system, as Voyager prepared to turn its cameras off permanently, engineers proposed a final sequence, a mosaic of planets, a wide-angle survey, a calibration experiment of sorts. Among those frames was one that barely registered as meaningful. A single pixel, slightly tinted, suspended in scattered light. Earth. At that distance, the signal arriving at the detector was vanishingly small. Reflected sunlight diminished with the square of distance. Cosmic background noise approached comparable magnitude. Instrument sensitivity approached its lower limits. The camera's dynamic range struggled to separate planet from glare. Stray light from the sun contaminated the frame. Contrast collapsed. This image existed near the threshold of detectability. Its survival depended on compression. Voyager's data rate at that distance was measured in bits per second. Images were encoded line by line. Color channels were downsampled. Brightness values quantized. Much of the original signal was discarded. What remained was a statistical reconstruction. Not a photograph in the conventional sense, but a compressed estimate of photon arrival rates mapped onto digital values. Earth became data, not geography, not atmosphere, not oceans or continents, a point. This reduction altered meaning profoundly. At planetary scales, complexity dominates perception. Atmospheric bands, storm systems, surface textures. At interplanetary scales, these details vanish. The same object transitions from structured system to unresolved emitter. Scale erases narrative. This is not merely aesthetic. It reflects a fundamental property of information. As distance increases, angular size decreases. As angular size decreases, spatial frequency collapses. High-resolution information disappears first. Only total flux remains. Planets become radiometric signatures. Habitability becomes invisible. Biology becomes undetectable. Voyager demonstrated this limit directly. At sufficient distance, Earth is indistinguishable from uninhabited worlds. Its oceans do not matter. Its biosphere does not register. Its technological activity contributes nothing. Only albedo and phase angle remain. Meaning collapses into brightness. This forced a conceptual adjustment in planetary science. Remote detection of life cannot rely on imagery alone. It must depend on spectral signatures, on disequilibrium chemistry, on statistical deviations from thermodynamic expectation. The pale point demonstrated a boundary in perception, not technological, epistemological. There exists a distance beyond which complexity cannot be resolved, beyond which interpretation becomes ambiguous, beyond which inference replaces observation entirely. Voyager did not cross that boundary physically. It crossed it conceptually, and then it continued outward, beyond the planets, beyond the termination shock, toward the region where solar influence weakens. Here, the mission entered a domain defined not by images, but but by fields and particles. The heliosphere forms as the solar wind expands supersonically into interstellar plasma. At sufficient distance, the pressure balances, the flow slows, a boundary forms. This boundary is not a surface, it is a gradient. Density increases gradually, temperature rises, flow velocity declines. Magnetic field orientations shift slowly. No single crossing event announces arrival. Instead, multiple indicators change incrementally. Voyager's plasma instrument had failed long before. Particle detectors remained functional. Magnetometers continued operating. Plasma density had to be inferred indirectly, from plasma wave oscillations triggered by solar disturbances, from frequency shifts in electron density modes. Each measurement carried uncertainty. The transition region extended across astronomical units. At some point, solar particle flux dropped sharply. Cosmic ray intensity increased. Magnetic field direction stabilized in a new orientation. These signals indicated passage beyond the heliopause, but the heliopause itself had no coordinate, no fixed radius, no sharp discontinuity. It expanded and contracted with solar activity. It warped with interstellar pressure. It fluctuated with magnetic reconnection events. Crossing it meant entering a regime, not a place. This altered the meaning of boundaries in space physics. Classical thinking favors surfaces, planetary radii, atmospheric edges, orbital limits. But heliospheric boundaries behave as transition layers. Properties change continuously. No singular measurement defines membership. Classification depends on thresholds. Interstellar space begins not at a line, but at a condition, where solar influence becomes secondary, where particle populations shift composition, where magnetic topology reorganizes. Our Voyager's crossing was therefore probabilistic. Multiple criteria satisfied gradually, no single timestamp definitive. Even now, definitions vary. Some prioritize plasma density, some magnetic field orientation, some particle energy distributions. Each yields a different boundary. This revealed something deeper about cosmic structure. Large-scale systems do not terminate cleanly. They blend into neighbors. They overlap dynamically. The solar system does not end, it fades. This fading has implications far beyond heliophysics. Planetary systems around other stars will interpenetrate. Astrospheres will interact. Interstellar media will mix. Isolation is temporary. Boundaries are negotiated. Voyager, in entering this region, became an instrument of transition science. Not studying planets, not studying stars, studying interfaces. Regions where regimes overlap, where models are least certain, where data are hardest to interpret. Here, perception is weakest. Signal-to-noise ratios decline further. Particle fluxes approach background. Calibration drifts accumulate. Instrument aging complicates interpretation. Radiation damage alters response curves. Thermal cycling degrades stability. Every measurement carries legacy uncertainty. Yet the data remain invaluable, because no other probe samples this regime directly. Voyager's instruments measure interstellar plasma density, magnetic field strength and turbulence, cosmic ray modulation. These data constrain models of galactic environments, star formation feedback, cosmic ray propagation. But they also demonstrate a final limit. Beyond this region, even signals vanish. Transmission power decays. Power from radioisotope generators declines. Thermal noise dominates. Eventually, communication will cease. The spacecraft will continue silently, but observation will end. This termination is not failure, it is intrinsic. Every instrument has a horizon. Every sensor reaches sensitivity limits. Every channel saturates with noise. Voyager shows that exploration is bounded not only by distance, but by information, by the capacity to extract signal from background, by the ability to compress without destroying meaning, by the threshold at which measurement becomes indistinguishable from randomness. The pale point and the heliopause are linked by this principle. At one extreme, scale erases detail. At the other, regime change dissolves boundaries. In both cases, interpretation becomes the primary act. What matters is not what is seen, but how data are framed, how thresholds are defined, how transitions are interpreted. Voyager did not simply leave the solar system. It revealed where perception fails, where categories dissolve, where observation becomes inference, where knowledge becomes conditional. And in doing so, it delivered perhaps its most lasting contribution. Not a map of distant worlds, not a catalogue of moons, not a measurement of plasma density, but a demonstration. That exploration eventually confronts limits not of propulsion, but of understanding. That beyond a certain point, the universe does not become invisible because it is empty. It becomes invisible because our instruments no longer possess the resolution to assign meaning. And at that boundary, discovery no longer depends on travel, it depends on interpretation. Before the exploration of the outer planets, planetary science was organized around isolation. Planets were treated as independent bodies, their evolution modeled as closed systems. Their histories inferred primarily from surface features and bulk properties. Change was considered slow. Equilibrium was assumed common. Activity was regarded as transient. This framework reflected both observational limits and conceptual inheritance. Classical celestial mechanics emphasized stable orbits. Geology focused on erosion and cooling. Atmospheric science assumed gradual loss and stratification. The solar system appeared as a collection of objects aging quietly in parallel. The outer planet missions disrupted this picture gradually but permanently. As data accumulated, no body could be understood alone. Jupiter's resonances sculpted asteroid populations. Saturn's moons controlled ring structure. Tidal interactions sustained internal heating. Magnetospheres coupled multiple environments into unified domains. Motion and interaction became central explanatory variables. This required a methodological shift. Models expanded from single-body thermodynamics to multi-body dynamics. Orbital evolution entered geological interpretation. Electromagnetic coupling joined gravitational analysis. Planetary science became a systems discipline. Instead of asking how a planet evolved, researchers asked how an ensemble co-evolved. Moons were no longer accessories. They became energy regulators, chemical reactors, thermal buffers. The architecture of a system now defined its long-term behavior more than the properties of any individual object. This change reshaped mission design. Flybys gave way to orbiters. Single encounters evolved into multi-year surveys. Isolated targets were replaced by system-level campaigns. Cassini did not study Saturn alone. It mapped rings, moons, magnetosphere, plasma environment, and gravitational fields simultaneously. Juno measured Jupiter's interior by tracking its effect on spacecraft trajectory. Galileo sampled magnetospheric plasma to infer subsurface oceans indirectly. Comparative planetology emerged as a formal discipline. Instead of treating each planet uniquely, researchers compared patterns across bodies. Volcanism on Io informed models of tidal heating on exoplanets. Titan's photochemistry shaped interpretations of early Earth. Enceladus guided hypotheses about icy moons beyond the solar system. Classification schemes evolved. Planets grouped by mass alone were insufficient. Energy budgets became central. Orbital architecture became diagnostic. This produced a new taxonomy: active versus inert, internally heated versus externally forced, radiogenic versus tidal. The solar system became a laboratory of controlled experiments. Each moon represented a boundary condition, each resonance a natural perturbation, each magnetosphere a coupling regime. The institutional impact followed. Mission proposals emphasized system context. Payloads diversified to capture interactions. Long-duration funding models expanded. Data archives grew multidimensional. Time series joined spatial maps. Particle distributions joined imagery. Field measurements joined composition. The field adopted computational modeling at unprecedented scale. N-body simulations replaced analytic approximations. Thermochemical models coupled with orbital evolution. Magnetohydrodynamics entered mainstream planetary research. Planetary science converged with astrophysics and plasma physics. Boundaries between disciplines softened. Yet the most profound transformation occurred in how life itself was conceptualized. Before these missions, habitability was defined narrowly. Liquid water on a rocky surface, moderate temperature, atmosphere with pressure within terrestrial bounds. This model derived from a single example. Earth. Outer planet exploration destabilized that assumption. Io demonstrated that geological activity does not require surface habitability. Europa revealed liquid water beneath ice. Titan showed chemistry without biology. Enceladus displayed hydrothermal signatures in isolation. Life could no longer be tied to surface environments. It had to be redefined functionally. Energy gradients replaced temperature as primary criterion. Chemical disequilibrium replaced atmospheric composition. Sustained flux replaced orbital distance. Habitability became a question of process. Is energy available continuously? Can chemical reactions proceed far from equilibrium? Are compartments stable enough for organization? Location became secondary. This reframing extended rapidly beyond the solar system. Exoplanet classification incorporated tidal heating estimates. Habitability indices included stellar activity and orbital eccentricity. Ocean worlds became primary targets. Even stars were reconsidered. M-dwarfs, once dismissed as hostile, became candidates if subsurface oceans existed. Rogue planets became plausible habitats if internal heating persisted. Life became detached from sunlight. Chemosynthesis moved from anomaly to central model. Hydrothermal systems became archetypes. This forced a philosophical adjustment. Life was no longer an environmental condition. It was a thermodynamic process, an organized pattern sustained by energy flow, independent of surface, independent of temperature regime within wide bounds, independent of stellar distance in principle. This definition unified biology with physics. Life joined the category of dissipative structures. Alongside convection cells, chemical oscillations, atmospheric circulation, but with replication. This perspective changed research priorities. Search strategies shifted from imaging surfaces to probing interiors. Spectroscopy prioritized redox pairs. Plume sampling replaced landers. Detection strategies emphasized disequilibrium signals, methane with oxidants, hydrogen with carbon dioxide, isotopic fractionation. Life became a statistical inference problem, not a visual one. These conceptual shifts fed back into technology. Instruments were redesigned to detect trace gases. Mass spectrometers increased sensitivity. Magnetometers targeted induction signatures. Autonomy increased to enable plume fly-throughs. Trajectory design favored repeated encounters. The legacy of the outer planet missions thus exceeded their discoveries. They restructured the discipline. They altered the definition of stability. They redefined habitability. They reorganized classification. They merged planetary science with systems theory. Most importantly, they changed how uncertainty was treated. Earlier science sought definitive answers, single histories, unique outcomes. The new science embraced ensembles, multiple pathways, probabilistic evolution, parameter-dependent futures. The solar system was no longer a solved system with unknown details. It was a dynamic network with emergent behavior. And life within this framework was no longer a rare exception. It became a possible outcome wherever energy flows persist long enough to organize matter. This did not imply ubiquity, but it eliminated parochialism. Earth ceased to be the template. It became one instance among many regimes. The outer planet missions did not simply expand geographic knowledge, they expanded the conceptual space of science. They demonstrated that understanding complex systems requires abandoning static categories. That interaction governs evolution. That boundaries are permeable. That equilibrium is temporary. And that life, at its core, is not a place to be found. It is a process to be recognized, wherever conditions allow matter to remain organized while dissipating energy over long spans of time. The exploration of the outer planets was never solely a scientific enterprise. It unfolded within political constraints, institutional alliances, budget negotiations, diplomatic calculations. From the beginning, no single nation possessed all the capabilities required. Deep space tracking demanded global antenna networks. Launch vehicles required shared manufacturing lines. Instrumentation drew on expertise scattered across continents. As missions grew in complexity and duration, collaboration became structural. European laboratories provided spectrometers, plasma analyzers, and radar systems. American institutions supplied launch systems, navigation, and operations. Data pipelines crossed borders continuously. This cooperation was not incidental. It reflected a shift in how knowledge itself was organized. Space exploration created infrastructures that no country could maintain alone. Tracking stations formed planetary-scale networks. Time synchronization depended on international atomic standards. Calibration relied on shared reference catalogs. Knowledge became distributed by necessity. Instruments built in one country were flown by another. Data archived in one agency were analyzed by researchers worldwide. Discoveries emerged from multinational teams operating across time zones. This altered the political meaning of exploration. Missions became diplomatic artifacts. Joint payloads required treaty frameworks. Launch agreements reflected geopolitical alignment. Data access policies embodied norms of openness. Scientific cooperation became a stable channel of interaction even during political tension. While strategic competition shaped funding, discovery itself resisted nationalism. Because no single archive contained the whole record, no single team mastered all interpretations, no single institution controlled all expertise. Planetary science evolved as a collective enterprise by structural design. Knowledge accumulation became cumulative across generations and agencies. This produced continuity rarely achieved in other domains. Voyager's data informed Cassini's targets. Galileo's magnetometer guided Juno's interior models. Huygens' descent shaped Titan exploration strategies decades later. Each mission inherited both hardware lessons and conceptual frameworks from its predecessors. Failures propagated knowledge as efficiently as successes. Radiation damage taught shielding design. Telemetry losses shaped compression algorithms. In-navigation errors refined trajectory modeling. This iterative accumulation resembled an extended experiment spanning half a century. No single mission defined the field. The field emerged from sequence, but collaboration did not operate only among institutions. It operated with the public. Because space exploration depends on sustained political support, and sustained support depends on imagination, images became instruments of policy, not through propaganda, through persistence. The first views of Jupiter's storms, Saturn's rings in high resolution, Titan's hazy horizon, Enceladus's plumes against black space. These images circulated far beyond scientific journals. They entered classrooms, documentaries, textbooks, museums. They constructed a shared mental geography. Generations grew familiar with worlds they would never visit. This familiarity mattered because funding decisions depend on narratives of value. Missions justified by long-term return required cultural patience. Budgets allocated across decades demanded public trust. Risk tolerated only when symbolic reward was visible. Imagery provided that reward, not merely as beauty, but as evidence. Evidence that distance could be crossed. That complexity existed elsewhere. That investment produced lasting knowledge. Scientific justification alone rarely sustains programs across political cycles. Cultural memory does. Voyager's images remained in circulation long after budgets ended. Cassini's final descent was broadcast globally. Hubble's deep fields became icons of modern science. These artifacts formed a durable narrative. That exploration expands identity. That knowledge persists beyond administrations. Unhid curiosity constitutes a public good. This narrative stabilized institutions. Agencies learned to present missions not as experiments, but as chapters in a continuous story. Long-term vision replaced isolated projects. Flagship missions were framed as generational endeavors. Archival strategies emphasized open access. Educational programs embedded planetary science into national curricula. Exploration became part of collective memory, not through technical detail, through imagery and framing. The pale point, the ring shadows, the plume silhouettes. These visuals did not explain. They motivated. They shaped which questions seemed worth funding, which destinations seemed meaningful, which risks appeared acceptable. In this sense, public imagination fed directly into scientific agenda. Targets that resonated culturally received priority. Missions with narrative clarity advanced more easily. Ambiguous goals struggled. This feedback loop influenced research directions subtly but persistently. Ocean worlds gained attention not only for chemistry, but because they fit emerging stories about hidden life. Rings received sustained observation not only for dynamics, but because they symbolized planetary structure intuitively. Exploration became selective not only by feasibility, but by resonance. Yet this resonance did not trivialize science, it stabilized it. By anchoring abstract research in shared imagery, the field secured long horizons. And with long horizons came patience. Patience to wait decades for results. Patience to maintain spacecraft long after design life. patience to analyze slowly evolving datasets. This temporal extension was essential. Outer planet science cannot operate on election cycles. Orbital periods exceed human planning horizons. Thermal evolution unfolds over millennia. Chemical equilibration spans geological time. Only institutions buffered by culture and collaboration can sustain such work. Thus, technology, politics, and public memory converged into a single system. Hardware-enabled data, collaboration stabilized programs, imagery maintained support, support enabled continuity, continuity enabled discovery. The outer planet missions did not simply map distant worlds. They demonstrated a model for collective knowledge, distributed, long-term, cumulative, public. They showed that some questions cannot be answered by individuals or even by generations. They require institutions designed to outlast their creators, and cultures willing to value knowledge whose payoff lies beyond immediate utility. This model has since extended beyond planetary science. Climate monitoring, gravitational wave observatories, large-scale genomic projects all borrow the same architecture: international coordination, shared infrastructure, open archives, public narratives. The outer planet missions therefore contributed not only data, they contributed a template for how modern science organizes itself around questions too large for any single community. In this sense, their greatest legacy may not be Jupiter or Saturn or Enceladus. It may be the demonstration that exploration at scale is possible only when technology, politics, and culture align around a common commitment. That knowledge, once treated as national capital, becomes more powerful when treated as collective inheritance, and that the deepest discoveries often require not just instruments and equations, but institutions capable of remembering across generations. The outer solar system did not overturn physics, it refined it. It showed that stability is not a default state. Every long-lived structure required continuous energy input, orbital resonances to maintain heat, tidal forces to prevent thermal collapse, magnetic coupling to sustain internal motion. Where energy flows weakened, activity faded. Where gradients persisted, complexity remained. Geology was not tied to size. Atmospheres were not tied to proximity to the sun. Oceans were not tied to surface warmth. Activity emerged wherever energy could be trapped and redistributed. This revised the meaning of habitability. Liquid water alone proved insufficient. Temperature alone proved insufficient. Distance alone proved irrelevant. What mattered was balance. Heat generation matched to heat loss. Chemical disequilibrium sustained over time. Structural integrity maintained despite constant dissipation. Life potential became a question of system architecture rather than location. At the same time, complexity separated itself from biology. Titan demonstrated that chemical networks can elaborate without metabolism. Ring systems demonstrated that structure can persist without growth. Atmospheres demonstrated that organization can arise without reproduction. Order no longer implied life, and life no longer implied surface worlds. The missions also revised scale. Small moons sustained oceans. Thin shells preserved heat. Weak gravity maintained circulation. Longevity was not proportional to mass. Durability was not proportional to size. Activity persisted in environments previously classified as inert. Finally, boundaries dissolved. Magnetospheres blurred into solar wind. Atmospheres transitioned gradually into space. The heliosphere faded into interstellar medium without a discontinuity. Edges became gradients. Transitions replaced borders. Systems did not end, they transformed. Taken together, these findings produce a quiet shift, not in what we know, but in how we define systems. Planets became processes, moons became engines, habitability became a balance condition, exploration became the study of persistence. No single discovery carried this message. It emerged only from sequence, from accumulation, from comparison, from seeing many systems fail in different ways. And a few persist under unlikely constraints. The outer planets did not reveal destiny. They revealed endurance. They showed how structures survive when equilibrium is impossible, how activity continues when resources are limited, how order is maintained without permanence. Exploration, in this sense, was not driven by answers. It was driven by uncertainty management, by testing assumptions about stillness, by replacing static models with dynamic ones, by observing how systems behave when isolated, heated, perturbed, and aged. What emerged was not a narrative of purpose, it was a framework. That persistence requires flow. That complexity does not require life. That longevity is not tied to scale. That boundaries are never absolute. And that habitability is not a property of place. It is a property of balance. This leaves one unresolved question. If stable activity depends on energy gradients and long-term regulation, and not on distance, size, or familiar conditions, how many systems remain active beyond current detection limits, quietly maintaining structure, sustaining chemistry, and persisting without observation?